All right, today we are going to start our two-section chapter. It's really sections 5.1 and 5.2 about integers. And before we get started too far, we need to define what integers are. So we've talked about whole numbers before. Remind me what you know about whole numbers. What are they? What's the smallest one? They're counting numbers plus 0. Okay, good. So our integers include all the whole numbers. So our 0, 1, 2, 3, and so on. Okay? But they also include the negations of all those same values but negative. So I have -1 and -2. And -3. And so on. Okay, so these are my integers. Integers usually show up in about 5th or 6th grade, depending on curriculum. The idea of integers, this idea of something being negative, shows up sort of conceptually far earlier than that, when kids start asking weird questions like, well, what is 3 minus 5? Right? And so please don't be the pre-K teacher that says that's not possible. Don't lie to your kids. Okay? Don't do that. I mean, if you want to answer something, be honest and just say you aren't ready to learn that yet or something. But those questions come up a lot earlier. I want to show you several different models for doing integers. We'll do integer addition first. For those of you who feel like math has been a pretty strong suit for you, you may have your ways of working with integers, and that's totally cool. Please be open to the idea that not everybody learns the same way, and integers especially, and then fractions when you get into proportional statistical reasoning with us here. Integers and fractions are really difficult for kids sometimes. And so having some concrete models and how to deal with that is a really useful thing. So the first thing we're going to look at is a chip model. So if I were teaching this in a real classroom, I would literally have something like poker chips. Okay? Maybe not if the school district said you can't have poker chips, but they'd look something like that. If not, they'd be colored little squares of paper. Okay? That's what I'd be looking for. In particular, it's really nice to use red and black because those sort of extend into other areas where red is negative and black is positive, like you've heard the phrase in the red or in the black before. In the red means that you've got negative, right, like you're in debt. In the black means that you're positive. We're about to hit Black Friday. Did you know that Black Friday is called Black Friday because for most businesses, that's the day when they actually start turning a profit at their business. That's when they become in the black, all the way from January 1st until November. Isn't that crazy? So I would encourage you to use colors. If you don't have red and black, you're welcome to use something else. In fact, if you don't have colors with you, I have colors. I'll pass them around. My other class. So I'm going to use black. I'm going to use red on my screen. And if you choose other colors, I just need to know what they're representing. So if you decide, absolutely, I want to use pink and purple, okay, but just let me know which one's positive and which one's negative, okay? So up, and make yourself sort of like a key. And it looks something like this. We're going to make what look like dots, chips. Imagine having like a poker chip. This is your image. So this one would be a negative. And this one would be a positive. Okay, everybody good? Okay. Actually, one of the cool things you can do as well, if you were actually using legit like poker chips or whatever, is if it's cheaper to do so, you can get the dots that you put on things, like sticker dots, and you can actually make one side of the poker chip one color and the other side the other color, and you usually need half as many poker chips because you can use them as double-sided. There's actually manipulatives that come that way too, automatically, if you're ever looking through like manipulative catalogs. All right, so here's what you're going to do. You're going to draw a circle. And inside your circle, you're going to represent 5 positive chips. Okay, so 5 positive chips would be 5 black chips. And you're going to represent the 3 negatives, and that would be 3 negative chips. So this is the starting image that your kids would be working with in physical form. If you were really doing this, I would encourage you to use physical form. This is a super concrete thing where they can actually display it on a placemat or whatever on their desk. Okay? 5 black chips, 3 red chips. And then you can talk about the fact that if you take a black and a red together and combine them, they form what's called a 0 pair. Okay, you guys like to use the phrase, I'm sure, cancel each other out, right? Right, but they add to 0 is the reality. One's a positive, one's a negative, and they add to 0. They're neutral. So every time I can pair up a positive and a negative, I will, and I will remove it. And again, if you were working with actual kids, you would take the black and the red and you'd physically move it off of the placemat that they were working with as many times as necessary until either only red or only black chips remain. And when you do that, so it would look like this in my picture, your answer then is to simply count what you have. This would be 2. There's 2 chips, and it's positive because the chips are positive. If you had 2 red chips left, it'd be 2 negatives, or -2 when you're done. Make sense? Okay. The next model is very, very similar. It's just that the images that we're using instead of black versus red are different. Okay? We're still going to do this idea of sort of putting things in and canceling out 0 pairs. This is called a charged fields model. Charged field model. So in this model, you have positives and you have negatives. So a positive represents a positive charge, and negative represents a negative charge. You can even talk about how batteries, you've ever done the batteries thing, you know? Like they go in one way and they don't go the other way. You know, the positives and the negatives have to actually attach to each other, or magnets, right? They repel each other or they connect to one another. Those kinds of ideas. So you're going to draw the circle again. And for the 5 positives, you're literally going to make 5 plus signs. That's 5 positives. And for the 3 negatives, you're literally going to make 3 negative signs. And you're going to, again, pair them up. A positive charge and a negative charge neutralize each other. And if you do that, you end up with 2 positive charges left, which is the number 2. Okay, so far so good? The addition of these is usually pretty straightforward, and we're all like, yeah, I get it. The subtraction ends up being trickier, so we will get to something trickier here in a little bit. There's a couple other models first I'd like to show you, though. One is called the number line model. The number line model works really well for your kinesthetic learners, the ones that want to move around. Not move just objects around, but their whole body around, and I'll show you that with mine here in just a moment. But let me show you what it looks like if I were writing it down on paper first, okay? So this says 5 on a number line. If I were at 5, I would be right here, right? And then this says -3, which would mean that I go backwards 3. And wherever I land, right, after that move backwards 3 is the number that I'm looking for. If you were doing this in, actual real time in a classroom, what I would do, I'm going to do it with desks, but I would encourage you to put masking tape on the ground and actually mark it out. I'm going to do it with desks. So this is my starting row, okay? And if I move 5 steps forward, 1, 2, 3, 4, 5, and then I move 3 steps backwards, 1, 2, 3. The question is, how far am I from where I began? And I'm still 2 steps to the right. Make sense? So we could actually work from a movement perspective with number lines, which is really cool. Probably the least widespread method would be our next one. However, if you think about some of the kids that maybe you have worked with before, there are kids who think in patterns. Some of our special needs kids really think in patterns. Think about autistic kids, stuff like that. Patterns are really, really valuable. So there are some kids for whom this is going to be a super useful way to do a problem. So again, all of these methods work really well when you're first introducing them. If you're doing something like 52 plus a negative 78, none of these methods are good. Y'all with me? This is an introductory level idea, not for computational down the line. Okay, so here's the way pattern models work. Patterns actually take something that we know is already true. So like if we've already learned about whole numbers and we already know, for instance, what is 5 plus 2? Well, we know it's 7, right? And if I just decrease that number by 1, well, what is 5 plus 1? Well, it's 6. And what is 5 plus 0? Well, it's 5. And I know all of that because that's prior knowledge because it's whole numbers. Everybody with me? That's old news. I know all of that. But if you take a look at what happens each time is that this value is decreasing each time in the middle, right? And if I continue that pattern by decreasing that, so that this is now 5 plus negative 1, and then 5 plus negative 2, and then 5 plus negative 3. So I'm decreasing the value in the middle every time. And I notice that there's a pattern on the right as well. The pattern on the right is that it decreases one every time. So I can continue that pattern, 4, 3, and 2. So in the end, that's the one that I want, and the answer would be 2. Okay? So you're starting with what you know, prior knowledge, and you're forming a patterned relationship within that number system, whole numbers, and then extending it into integers. All right, so when we get to our presentations, and you guys are looking to what you wanted to do for your presentations and so forth, let me just make a comment that your presentations are not intended to reteach material. So if you did any of what I just did as your presentation on the last 4 problems, that would not be appropriate. Your presentation is supposed to create context. So if you were working with any of those last 4 problems, you should be able to create context for them where the answer still looks like my problem. Okay, you're going to create your own numbers, but you could do that, right? So if I were working with this number right here, we could talk about the fact that I have 5 apples, right? And then Julie comes and she takes away 3 of my apples. How many apples are left? And we could represent that with, a number line model or with a pattern model or whatever, okay? So we could actually talk about, taking steps forward and backward, which would look really awesome with a number line model because I actually showed you that in action, right? I take 4 steps forward, and if I go backwards 3 steps, how far am I from where I started? So you're going to create context for what you're doing, not just using numerical examples. Are you with me on that? Okay, so this is one section in particular where I have very, very little context in my notes. And when people start doing presentations for it, they get a little flustered because they're supposed to have context, but you should still be able to do that. Okay, moving on a little bit, we'll come to the subtraction part. I think maybe even next time. I think that we're going to do a couple other things before we get there. Yeah. Absolute value is where we're going to start. So an absolute value for any integer x. So the absolute value of x is equal to x if x is positive or 0, and it's equal to negative x if x is less than 0. People get a little concerned when I post this on here because it looks like I'm telling you the absolute value is a negative number. It isn't because x itself is already negative. So if you had a negative number, let's say that x was negative 3, and you wanted the absolute value of negative 3, this actually says you should do the opposite of negative 3, which would be what? 3. Okay? The opposite of negative 3 would be 3. So this description on the second line is not saying it's a negative. It's simply notation telling you how you get the negative to go away. You just multiply by another one, right? You take the opposite of it. Any of those kinds of descriptions. Now, what is an absolute value really, though? Well, an absolute value really is distance. It's really distance. It's the distance back to somewhere else. So in terms of just like concrete numbers that we use in class, we're usually talking about the distance back to 0. But if you talk about like when I commute from my home to school every day, right? That's a distance. I don't say that I drive 20 miles here and negative 20 miles home. We don't talk like that, right? Distance is always positive. Absolute values is our application, or distance is our application of an absolute value. It's always a positive concept. So we're going to take a few examples. I'm going to let you give your try at doing these first. We're going to classify them as true or false. And if you believe it's false, show a counter example. Okay, so hopefully you've got a pencil you can write these down with because you might guess wrong. But take your best stab at A through D. Is it true? Is it false? And if it's false, show an example why. And most of you are not writing, so if you're finished, see what your neighbor says. And if you disagree, see if you can figure out why. Okay, how about the first one? What do you think? True, it is true. I didn't ask you for the why before, but does anyone have sort of an argument why they believe that's true?
Because it's the same distance. Like, if you put a number into, like, if you do 2 to the 4th, absolute value of 2 to the 4th, it's the same as...
Okay. So hold that thought for me, Kimberlyn. Let's actually answer part B, and then we'll go back to part A and add to what you've said. What about part B, true or false? It's actually false. Okay, so for those of you who said false, how is B different than A?
So your exponent is odd.
Yeah, that's what I'm hearing. Okay, good. So the exponents matter, right? Why do they matter? What difference does it make? Ah. Okay, so when you have an even exponent, and that's the kicker that we're going to add to what Kimberlyn said. On the first one, x to the 4th is greater than or equal to 0. And the reason is because when you multiply something by itself, it's always positive, the solution, right? The product is always positive. So if you have a negative times a negative, it's a positive. We're going to talk more about these when we get to the next section, 5.2, but I know you guys know this. And if you have a positive times a positive, it's also positive, right? So x to the 4th is always greater than or equal to 0. And if you take a look back at what we just said, the absolute value of x is equal to x when x is positive, right? So the absolute value of x to the 4th is going to equal x to the 4th because x to the 4th is positive. The problem, of course, on part B is that there are not always there are values that are not always positive when you take something to the power of 5. Did anybody have a counterexample? What did you let x equal? Or what could you? -2. Okay, so if you let x equal -2, -2 to the 5th is actually equal to -32. And that's what would be on the inside here, right? And the absolute value of -32 is not -32, right? That's why that doesn't work. C and D. All right, what'd you get on C? True. And we'll come back to it in a second. These go together. What did you get for D? How are C and D different? Or are they? Does not negative mean the same thing as positive? So not negative means that it could be positive or 0. Is an absolute value always positive or 0? Yes, it is. It is. A distance is always positive or 0. But part D says the distance is always positive. Is that true? No, it's not true. It's not very exciting. It's false. The example is if x itself is equal to 0. Right? If I talk about how far I'm away from my home and I'm sitting in my bedroom, the answer is 0. I'm not far away from my home. I'm still in my home. Right? That distance is still 0. Good job. All right, we've got some properties. We've seen these properties before. This is not the first time around the bend. We've done this in chapter 3. It was when we were talking about whole numbers, and all the properties are the same, and we get more. So the first one is the closure property. So if you remember, closure is the one that always trips us up visually or like mentally when we're thinking about it. Closure means if I take 2 items in a set, and this time we're talking about integers, and I add them together because we're talking about addition, do I still end up with a number in the set? In other words, is an integer plus an integer always another integer? Absolutely. Right? Absolutely. If you add a positive number and a negative number, you always still get the same type of number you were working with, right? In this case, we're talking about integer numbers. So the closure property says that if you take 2 integers, a plus b, this is a unique integer. Just like we could do with whole numbers and natural numbers and even numbers, right? Even plus an even is even. Commutative property of addition. What does the commutative property say? You got it. A plus b is equal to b plus a. Works for integers just like it worked for whole numbers. The associative property. That one has to do with parentheses, just like distributive has to do with parentheses. And it looks something like this. If I group the b and the c together, and I leave the order the same, but then I group the a and the b together, it makes no difference. The order of my addition, the grouping of the ordering of the addition, none of that matters. It works the same way. And it works for whole numbers just like it works, or for integers just like it worked for whole numbers. Identity property of addition. We had that before. Do you remember what the identity element is for addition? It's 0. And it works for whole numbers as well as now it's working for integers. 0 is the additive identity such that 0 plus a equals a plus 0 equals a. You add 0 to something, it doesn't change it. It's not very exciting. Here's our new property. We now have something called an additive inverse. The additive inverse says the following. For every integer a, there exists a unique integer negative a, or the opposite of a. It's called the additive identity, or I'm sorry, the additive inverse, of a, such that a plus negative a equals negative a plus a equals 0. So somebody give me an integer, anything you'd like. 3. What would the additive inverse of 3 be? Negative 3. Okay? And any integer you give me, I can do that for. Somebody give me another integer. 14? 14. What's the additive inverse of 14? Negative 14. What if we started with, say, negative 7? What's the additive inverse of negative 7? 7. Okay? How about this one? What's the additive inverse of 0? It's 0. It's still there, okay? Still there. So why did we not have this property before? That's exactly right. We didn't have negatives before, right? When we were working with whole numbers do not include negatives. So there were no additive inverses because there were no negatives. You guys with me? So sometimes you'll hear in the integers defined as the whole numbers and their additive inverses. The whole numbers and their additive inverses. It's another way of defining them. Okay, so I have one more theorem and then we'll pause for today. And we'll pause for today. That's a good place to stop. Theorem 5.3 talks about what happens when we have certain types of, symbols, I guess. We talked about this one already. This is the opposite of negative a, or the additive inverse of negative a, and that would be a. So this double negative business that sometimes happens when we do mathematics actually ends up being positive, because the opposite of a negative is a positive. That's why that's happening. If we have two numbers that are equal, or two values that are equal to begin with, and we add something to both of them, they're both still equal. My 13-year-old daughter and I are just about the same height. It's pretty close now. It's craziness, actually. And if we go both put on, our 2-inch heels for our boots or whatever, we're still going to be the same height, right? It's not going to change it. Now, if I go put on heels and she doesn't, that changes it. Okay, but if we add it to both of our heights, then we are still the same height. The last one talks about what happens when you're adding together numbers that are both negative. And we'll look more at this from a concrete perspective next time about what happens when we're dealing with subtraction and addition of negatives going on. What this is telling you is that if you have the opposite of A plus the opposite of B, it's really just the opposite of A plus B. Okay, so that's really good to know, because if you already know your addition facts, like flashcard facts for addition, then you don't have to relearn them when you're dealing with negative integers, right? You don't. All you have to know is the same thing you already had, and then the signs are different. And that's really cool. So that's our last one on here.